So optics is the study of electromagnetic waves and light waves, and these are not mechanical waves, but they demonstrate all of the properties that waves have, like diffraction, refraction, reflection, transmission, all of that. We'll go through them one by one. What these waves are, these electromagnetic waves, are oscillating electric and magnetic fields. They do not need a medium to travel through, so they can travel through the vacuum of space. Quite often we're talking about visible light, but remember, anything on the electromagnetic spectrum, so if it's X-rays, UV, infrared, gamma rays, all of this is going to have exactly the same properties as the light waves. So one of the first things that we talk about as a wave property is the velocity of that wave. So velocity is equal to wavelength times frequency, and the velocity of an electromagnetic wave or a light wave in a vacuum is 3 times 10 to the 8th meters per second, which is the speed of light, which is given the letter C. And that is the same as the velocity in air, but as light moves into other materials, it actually slows down. And in order to determine the ratio of the speed of light in a vacuum to the speed of the velocity in a new medium, that ratio is called the index of refraction, which is given a letter n. And so it's the speed of light over the velocity. N can never be less than 1, because you can never have a velocity in a new medium that's greater than the speed of light, so this fraction would never be equivalent to anything that is less than 1. All right, so at boundaries, we know that light both reflects and transmit, or any wave will reflect and transmit as it encounters a boundary. If we're talking about reflection, and I'll go more into detail about mirrors here in a second, but if something encounters a mirror, the angle that it is incident upon that mirror is going to be equal to the angle of reflection. So if this is my mirror right here, and the light comes in and it strikes the surface, there's something called the normal line that is perpendicular to the surface at that point, and the angle of incidence is measured to that normal line. So as the light bounces off, it comes up, and you are going to have the angle of reflection, being equal to the angle of incidence. Now, as the light encounters this new medium, sometimes this medium here has a different index of refraction. If the N1 of this material, where it's coming from, hits an N2 that is greater, right? So where an N1 is less than N2, so like if this was air and this was water, that's considered a fixed boundary. So when the things reflect off of each other, there is a phase change, just like when we saw with sound waves or mechanical waves, that the wave inverted itself. And this will come into play when we talk about thin film interference at the end of this video. Now, if we go from an N1 that is greater than an N2, so let's say the other way around, let's say we've got, oil and air, then when the light reflects off of that boundary, there's going to be no phase change. This is like a non-fixed boundary, right? However, whenever anything encounters a boundary, whether it's fixed or non-fixed, some amount is going to be reflected and some amount is going to be transmitted. So that energy is actually going to be split. So the intensity of the rays either being reflected or into the new medium are going to be dissipated because there's only a finite amount of energy coming in. All right, so as light transmits into a new medium, it's going to pass into that new medium, and we know that when light enters a different medium, the velocity is actually going to change. And when the velocity changes, the light bends, and this is actually called refraction. So in the new medium, when light passes in the new medium, the velocity changes, but frequency does not. Frequency stays the same. So if we look at our wave equation, if velocity goes down and frequency stays the same, that must mean the wavelength must also decrease. So to find the wavelength in a new medium, you just take the wavelength of the light incident on that medium and divide it by n, the index of refraction. And again, this will come back when we talk about thin film interference. But let's go ahead and go back to this reflection and transmission and talk about it in terms of mirrors and lenses to start. So a mirror is something that reflects light, and lenses transmit or refract light or bend light, right? And the whole purpose for both of them is to create images. There are two equations that can be used for both a mirror and a lens, and they are the same, but we'll distinguish what makes things different in terms of mirrors and lenses with our rules in a minute. So the first, for the equations, it says 1 over the position of the object plus 1 over the position of the image that is created must be equal to 1 over f, which is the focal length. And then the magnification of the image that is created must be equal to negative the image distance over object distance. Magnification means like how much bigger it is. So if the magnification ends up being 2, it means it's 2 times bigger. If the magnification is 0.5, it means it's half the size, right? We'll also learn something about what magnification terms means in terms of like right side up or upside down or real and virtual and all that. All right, so if we were to have a mirror, right? So we're really dealing with curved mirrors here, either convex or concave mirrors. So here I have a mirror, and if there's an object over here, right, this curving at the object, this is a concave mirror. If it was to go the other way, that would be a convex mirror. So there is a curve that would be completed by some circle there, and so the center of whatever that circle is called the center of curvature, and then 1/2 of that is called the focal length. Now if the mirror is curving the other direction, then you know the center of the mirror is going to be over here and the focal length is going to be over there. This is my object right here, so the light bounces off of that object, hits the mirror, and then comes back and creates an image. If the image is on this side of the mirror, because mirrors reflect light, this is considered to be real. Whereas behind it, if it creates an image over here, it is said to be virtual. For a lens, it's the opposite. So for a lens, we're going to have focal points. You're actually going to have one on each side for this thing. And the center of curvature ends up being in the very middle of the lens. Right, and light actually, lenses actually transmit light. So as light bounces off this thing, it goes through it. So if there's an image created over here, it's said to be real, whereas there is an image created over here with a lens, it's said to be virtual. So let's go ahead and look at our rules, right? So if you can memorize this, then you'll know everything there is to know about solving for mirrors and lenses. If you have a positive magnification, you're upright. If you have a negative magnification, you're inverted. It doesn't matter what kind of mirror it is. If your image distance ends up being positive, you're real. If your image distance ends up being negative, it means virtual. Now remember, for each type of thing, whether it's a mirror or a lens, it's going to be different what side it's on, but the sign convention still remains. When we have a concave mirror or a converging lens, the focal length always needs to be made positive in the equation. And if you have a convex lens or a diverging, or convex mirror or a diverging lens, the f always needs to be plugged in as negative, right? So remember, if you're positive, you're real, upright, and concave. If you're negative, you're inverted, virtual, and convex. All right, so there's 3 rules for drawing ray diagrams in order to show, like, sort of geometrically where an object is going, or where an image for an object is going to appear. The first one is really kind of number 2 on this sheet, but it should always start with the object, go parallel to the principal axis, and then through the focal point. So if I show an example down here, I'm only going to do one ray diagram example, and then we're going to move on, but there's more videos if you need help with them. So here is the object right here. So parallel to the principal axis, hits that mirror, and then bounce back through the focal point, right? And we always draw a virtual ray out the back of the ray that reflects or refracts. So that's the first one. The second one goes through the focal point, or connects the focal point and the object, and then bounces parallel to the principal axis. So for this one, our focal point is here and the object is here. So this line connects it, but when it encounters the mirror, it reflects back parallel to this, which is the principal axis, and then my ray goes here. And then the last one, just to double check, should be through C and back. So here's C, and it goes from the object and then bounces back in another virtual ray over here. So this is where they cross, and this is where the image would appear. We could also figure out the distance and relative size and position all from using our equations and, using these concepts here. All right, so again, there's more ray diagram videos if you want to go back and watch them, but let's kind of move forward by talking then more about refraction. So as light enters into a new medium, it is either going to speed up or slow down, right? So as light is incident on, here's the interface between the two mediums, N1 and N2, right? The angle of incidence is the same as it was for reflection, and it's perpendicular to wherever the light strikes the interface. Snell's law says that the index of refraction of the first medium times the sine of the angle of incidence will be equal to the index of refraction of the second medium times the sine of the angle of refraction. If the light bends towards the normal, that means that N2, or this medium, is greater than N1. The velocity of the light is decreasing and it bends towards your normal, right? Now, if we look down here, we've got an angle of incidence here as it comes in, and as the light passes into the second medium, it zooms away from the normal. If you go away from the normal, then it's opposite of this stuff. If you go away from the normal, that means your velocity is actually increasing as you move into that new medium, and instead of N2 being greater than N1, N2 would be less than N1 in this incidence. Right? Now, if you wanted to figure out the angle, or you wanted to figure out the index of refraction of some unknown material, you could use the relative angles and plot it on a graph. So let me kind of zoom in because this graph is kind of small. So if we used air as the first medium, remember that air actually has an index of refraction of 1, so it makes this essentially cancel out. So N2 just ends up being a ratio of the sine of the angle of incidence to the sine of the angle of reflection. So if we were to change the angle, we could plot and then measure the refracted angle and plot the sine of the angle of incidence here and the sine of the angle of refraction here, and so the slope of the best fit line of this graph would be give us N2. Also, where the sine of the angle of incidence is equal to 1, that would give us the critical angle. So what is a critical angle, right? So the critical angle can happen only when you move from an index of refraction that is greater than the index of refraction it's entering into, right? So N1 here is greater than N2. We will see a critical angle. So we can see that if we were to keep increasing the angle of incidence, at some point the refracted ray would run parallel to the surface, and if I went any further, it would actually bounce back into the medium from which it came. This is called total internal reflection. And to find that critical angle, or so that point where it runs parallel, we do the sine of the angle of the critical angle is equal to N2 over 1. And again, this N1. And again, this only happens when N1 is greater than N2, right? So then we have, actually I'm going to hold off and just make a second quick video that's going to talk about diffraction and thin film interference because I'm going to run out of time on this one.